We're going to do our first example problem of basically looking at a material with strain gauges in a certain configuration and figuring out when there's a combination of tensile and bending or thermal stress, when can we eliminate or not measure the thermal contribution, the bending contribution, or our kind of typical other normal stress contributions, because remember our strain gauges can only measure normal stresses and strains. So let's go ahead and write this out. So quick apologies here for this. So this coordinate system should be 2 and 1. So let's go ahead and write those these expressions out here. So we have clearly some bending that's popping out of the page, and we have some stress 0, 0, 0. This is our stress tensor. Always good to write this out for partial credit here. So this is our stress tensor. There's only kind of one contribution, is this normal stress in the 2, 2 direction, and we have our strain gauges all aligned in the 1, 1 direction. So I have my strain in the 1 is equal to my strain in the 4, which is going to be equal to, again, some positive bending, because again it's popping out of the page, so that strain gauge is elongating, minus, or actually plus, whatever the strain in the 1, 1 direction is. And the strain in the 1, 1 direction, again, just given by our equation 66, strain in the 1, 1 is equal to 1 over E times minus nu sigma 2, 2. That's it. I also know that I have a strain in the 2, 2 direction, and that is going to just be equal to sigma 2, 2 E, and I'm going to have a strain in the 3, 3 direction, which is going to be equal to, again, minus nu sigma 2, 2 over. That's it. So we're not kind of interested in these out of the contributions, but these are going to be the two strains, and so this is our E11. So that is equal to this, and then for our E2 is equal to E3, or epsilon 3. The only change here, we're still measuring the strain in that 1, 1 direction, but now we have negative bending. Why? Because again, the dashed, if you see kind of these dashed, not full, rectangles here, if you see dashes, that means it's on the back of the page. So if we're bending and it's popping out of the page, that means on the back of that material, on the bottom, it is being compressed. So that's why we have this negative bending contribution here. So if I add all of those contributions up, oh, what have I forgotten? The most important one, this epsilon t. That's epsilon t. So our thermal strain contribution is always alpha delta t. So we need to include that. So I can write out the full expression now. So if I do my delta v naught over bi is equal to f over 4 of, so let's just add those contributions together, and we'll see that if we add these up, I'm going to do my EBs are going to be 4EB, and you see positive strain here, so these are going to be plus 2, these are going to be again epsilon 1 minus epsilon 2 minus epsilon 3, so these are negative. So again, this turns this into positive 4EB. The E sub 1s are going to cancel. So if you write those out and just kind of do the math at this point, and then because these are positive, well, those are going to cancel. So this is the only expression that I have left. So for this equation, all I'm going to get is V naught Vi equals F EB. That's it. So I am basically, in this configuration, I am not measuring this kind of. There's no contribution. If I arrange the strings in the strain gauges in this configuration, I'm not able to measure the contribution of strain to basically transverse or this normal stress in the 2, 2 direction. So I cannot measure that strain. There's no kind of axial contribution. There's no E111 contribution. The only thing in here is bending. So in this configuration, I've eliminated my axial strain components, and I've also eliminated my temperature components as well. So let's figure out a configuration that can eliminate my bending components. So let's go ahead and see, and actually let's try to figure out one that also gives us a non-trivial answer. Because you can see if I switch, let's say for example, I switch this, and then here. If this happens, what's going on here? So now let's just look at bending. So E1 is equal to E2, which is equal to E bending, and then E3 is equal to E4, which is equal to minus E bending. So if I add that up using this expression right here, my total strain, E1 is EB minus EB, E3 is minus EB plus minus EB. So that's going to end up with a null contribution. So if I have to use all without having a null contribution for the axial strain components, or just again the normal strain components, let's go ahead and look at that, a configuration that can do that. But unfortunately, for a full bridge configuration, we're never going to be able to basically have a thermal contribution, and you can kind of see that in just looking at the math, because that's always going to be this positive. Your thermal strain is always going to be this alpha T. So with 4 strain gauges, possible. But we can get rid of bending, but then also eliminate the bending contribution. So let's go ahead and draw that one out right here. So again, this is my system. So I have stress in the 2, 1. So stress in 2, 2, popping out of the board. And what if I do this? So I have 1, I have 4, and then I have flipped 2, and then 3. So let's write that out. So 1, I have positive bending, plus I have this strain in the 1, 1. In 2, actually in 4, I have negative bending, plus the strain in the 1, 1. In the 2, I'm going to have minus new EB. Why is that? Because as I bend, the material wants to elongate this way, and the wires are going to shorten. Some contribution minus new EB. So that is, again, because that's the contribution. In pure bending, that's what you're kind of going to deal with. And then I also have my plus E22. And for the 3, it's going to be, the sign's going to change. Why? Because on the back now, when we're popping out, again, it's going to compress here, and your wires are going to jump up that contribution EB plus E22. So if I add all those up into my kind of fundamental expression, so E1 minus E2 minus E epsilon 3 plus epsilon 4, you see that these are going to cancel, these are going to cancel, and these will also cancel, actually minus minus, so that's going to be plus. So I'm actually, what I'm going to end up with is 2 epsilon 1, 1 minus 2 epsilon 2, 2. That's it. So I can eliminate bending and only have this axial contribution. And again, this E alpha over 2 is always tacked on, but again, that gets canceled out. So next time we're going to get into thin-walled pressure vessels. So I'll see you in the next video. And hopefully, again, you can expect to see a problem like this in your problem set, and also most likely on an exam problem as well. So I'll see you in the next video. Thanks. Bye.